All right, gentlemen, good morning and happy whatever today is. Thursday, April the 2nd. Um, so today I am doing the second version, hopefully the right version, of the video on electric current. Um, and so that's where we'll begin. Um, so, what is exactly electric current? Everything that we've talked about thus far has dealt with really static electricity, where charges are gathered or held in one place and then uh, maybe pushed or moved or whatever. All right. However, the electricity that we usually think of when we say something is run by electricity is what we call current electricity. All right. This means that the electric charges are moving from one place to another. Now, two things I want to point out there. First, all right, when you're talking about an atom of a metal, okay, what charge is actually moving? It's not the protons that you find in the nucleus. It's the electrons that are surrounding the nucleus that are free to move from one atom to another. And in a metal, if you recall from Mr. Leonard's chemistry class, there's this sea of mobile electrons, and they are able to move freely uh, down the length of a conductor. So electric current, which is symbolized weirdly enough with a capital I, exists when electrons move through a conductor. And they always move from where they are, the negative end, to where they ain't, which is obviously the positive end, because of course negative charges are attracted to a positive charge. The units of current are given as amperes. All right, this is named after the famous physicist Joe Ampere, and is therefore abbreviated with a capital A. Okay, and 1 ampere is equivalent to 1 coulomb of charge per second. All right, so that means that there's 1 coulomb of charge zipping through the wire each and every second. That gives us the formula I equals delta Q over delta T. Current equals change in charge over change in time, which you can find on your handy dandy New York State reference tables. It's located right here. Okay. Anyway, moving along. Example number 6. All right. So let's use this formula that we talked about in the previous slide. All right. We'll start with this question. What is the current flowing through a wire if 3.00 times 10 to the 18th electrons pass through it each second? Now, we're looking for current. We know the number of electrons and we know the time. We'll assume the time is 1 second. But there's no charge here. So what's the key? All right, once again, we're going to turn to our handy dandy reference tables, because on the front page of the reference tables, there is what we call one elementary charge. All right, and that is the charge on one electron. All right, one electron. So let's go through this here. All right. Obviously, the question is, what is the current? So I is my my big fat question mark in this case. Now, I don't know. I know the time, but I don't know the charge. So I don't know why this is not popping up. So the number of electrons is 3.00 times 10 to the 18th. Now notice there's no unit there because this is a constant. It's a number, all right? It's a count, if you will. And I know that the time elapsed that I'm choosing, why not keep everything easy, is 1 second. Now, okay. I don't know what's going on with the timing on this PowerPoint, but here we are. The charge is therefore going to equal one elementary charge. That's this number, which we find on the front page of our reference tables, 1.60 times 10 to the negative 19th coulombs. And I multiply that by the number of electrons that I have, which is 3.00 times 10 to the 18th. And that gives me a total charge, come on, total charge of 0.48 coulombs. Now, that doesn't answer the question, because the question is, what is the current? And the current is equal to delta Q over delta T. Damn it. Delta Q over delta T, which is 0.48 coulombs per 1 second, which is 0.48 coulombs per second, or 0.48 amps. Now, this brings us to the rules that govern electricity. So anybody who's going to work with electricity, whether it's in the house or your electrician, for example, needs to be somewhat aware of the formula that we're about to talk about, because this is going to govern the relationship between the voltage that we talked about yesterday and the current that we talk about today. And this is known as Ohm's Law. I don't know how this is working out here, but so Ohm's Law states that at a constant temperature, the current in a metallic conductor, all right, a wire, in other words, is directly proportional to the potential difference between its ends. So if I was to graph this, all right, if I've got V and I've got I, it's a direct proportion. Bam, there we go. Now, the proportionality constant here is called resistance, and it is abbreviated with this letter omega, which is the last letter of the Greek alphabet. But it sounds like, damn it, ohms, and therefore we use it as the symbol for this. So ohms are not symbolized with an O, they are symbolized with an omega. All right. That brings us to example number 7, all right? Easy peasy example, I hope. In this case, we're going to start out, of course, looking at Ohm's law. So what is the current through a 30 ohm resistance that has a potential difference of 120 volts? Okay. What is the current through a 30 ohm resistance that has a potential difference of 120 volts? All right, so again, in this case, just like in example 6, we're going to start by looking for the current. So the first thing on my laundry list is going to be I equals a big fat question mark here. Now, I also know in this case that the resistance is 30 ohms, and the potential difference is 120 volts. Now, the formula that I know is V equals I times R, which, by the way, is found on my handy dandy reference tables on the electricity page. Again, it's located just below the current equation. All right, so there it is. It's written in a slightly different form, but it is the same. But V equals I times R. Now, that leads me to an algebraic rearrangement of I equals V over R, which is 120 volts divided by 30 ohms, which gives me 4.0 amps. Two significant figures. Okay. Now, what are the rules that govern the resistance in a conductor? Okay, and there are certain very important rules that we need to keep in mind here. Okay, first, the length of a conductor plays a role here. Imagine trying to drink through a straw. Okay, if you've got a straw that's only that long, it's going to be fairly easy to draw the fluid up out of your cup. Okay, if you've got a straw that's much longer, like one of those crazy straw, I don't know what is going on with this, but anyway, like a crazy straw, it's going to be harder. So as the length increases, the resistance increases as well. Now, in terms of cross-sectional area, in other words, the diameter of the circle that you're pulling through, all right, a little circle is going to be fewer electrons are going to be able to get through at any given moment. But if you increase the diameter of that circle, or the cross-sectional area of that wire, more electricity is going to go through. That's why the wires in your house are very narrow, but the big wires, the transmission wires that you see running along highways and that sort of thing, have a much greater diameter. They can carry a lot more electrons. So as the area increases, the resistance decreases. Finally, temperature also plays a role. As temperature increases, R increases as well. All right, that's why in the summertime we often have these rolling blackouts because it gets more difficult to move electrons through a hot wire than through a cold wire. Now, the formula that relates this all is shown here on the bottom of the page. Again, this is found on your handy dandy reference tables. It's right, where is it? Here, okay? Resistance is equal to resistivity, that's this funky looking little letter here that we call rho, times the length divided by the area. And this is at a given temperature. As a matter of fact, once again, on your reference tables, in this corner, you see resistivity at 20 degrees Celsius for a number of given common conductors, okay? And so that's the number that you find on this table is the resistivity value that you see here. This brings us to example 7a, okay? So here, I'm going to be looking for the resistance in a wire, all right? So I want to find the room temperature resistance of an aluminum wire 100 meters long with a radius of 1.00 millimeters, okay? So let's have a look here. We start out with example 7a. So we're looking for the room temperature resistance. So R is going to be my big fat question mark, but I know that it's an aluminum wire. So I immediately go to my reference tables. I look up the resistivity value for aluminum, and it turns out that it's 2.82 times 10 to the negative 8th ohm meters. The length of the wire was 100 meters. The radius of the wire was 1.00 millimeters. Now I'm immediately going to convert that to meters. So it's 1.00 times 10 to the negative 3rd meters. But that still doesn't tell me the area, which I need for my resistivity formula. So I have to use the formula for the area of a circle, cross-sectional area of pi r squared. So pi times the radius squared, 1.00 times 10 to the negative 3 squared, gives me 3.14 times 10 to the negative 6th square meters. Now, I then go to my formula for resistance, and I forgot to, this should be rho, not R, but R equals rho times L over A, 2.82 times 10 to the negative 8th ohm meters times 100 meters divided by 3.14 times 10 to the negative 6th square meters leaves me with a grand total of resistance of 0.898 ohms. Okay. Your homework for this will be due on Tuesday of next week. Tuesday, April the 7th, is going to be questions 8 through 11 on the electricity homework sheet. All right, gentlemen. Happy Friday or Thursday, whatever today is. Today's Thursday, April the 2nd. Have a don't forget you have a quiz tomorrow. This stuff will not be on that quiz. And I will talk to you soon.